So we've been talking about some different types of reactions, and now we're going to talk about oxidation-reduction reactions. These are reactions in which electrons are transferred from one reactant to another during the course of the reaction. They're also called redox reactions, for red reduction and ox for oxidation. That always reminds me of red box without the B. Many, but not all, redox reactions involve something reacting with oxygen. These are also called combustion reactions. And this is one we've looked at before. Burning octane requires oxygen and produces carbon dioxide and water. And that's an oxidation-reduction reaction. Here we show the redox reaction between hydrogen and oxygen. So in this balloon, we have a mixture of oxygen and hydrogen gases. And when we initiate this reaction with a spark, they combine rather violently and form water. In this process, electrons are transferred from one substance to another, and that's what defines a redox reaction. You can also have redox reactions without oxygen. Here's the reaction between sodium metal and chlorine gas. So here we have a little chunk of sodium metal in a container with chlorine gas, and these will react by transferring electrons. Electrons will be transferred from the sodium to the chlorine, and that will result in sodium chloride being formed. So if we look at the reaction of sodium with oxygen, this fits the description of a combustion reaction because we've got something reacting with oxygen, and we form a sodium oxide. We also have a reaction between sodium and chlorine, and this doesn't look like a combustion reaction, but it is a redox reaction. These are reactions between metals and nonmetals. So if we look at what's happening here, in both of these reactions, we have the free element sodium and a free element nonmetal, here oxygen and chlorine. And what's happening is the sodium is transferring an electron to oxygen. And so here we have the formula. This looks kind of messy, doesn't it? Because this is a formula for a compound where they're showing the charges. And that kind of illustrates why we don't show charges in compounds. It gets a bit hard to look at. But we do it here to point out that these are sodium ions and oxide ions. They started out as atoms. And here, sodium and chlorine, again, the sodium is transferring an electron to the chlorine, forming a positive and a negative ion, and the result is an ionic compound. There's a transfer of electrons. In order for a free element to become an ion, there has to be the gain or loss of electrons. And if one atom loses electrons, another atom has to gain them. There's no electron bank where you can go and just make a withdrawal, and there's no electron shelter where you can donate unwanted electrons. It has to be a direct transfer from one atom to another. So oxidation and reduction always go together. If there's one, there has to be the other. So the atoms that lose electrons are being oxidized. Atoms that gain electrons are being reduced. That can be a little hard to remember. And so we use this mnemonic oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. Oil rig. And you know, unless you deal with oxidation reduction a lot, you just don't remember this. And so, you know, I'm a chemistry teacher, and I still think oil rig to myself before I state out loud, is this oxidation or reduction? So here we have the sodium and the chlorine. What's happening, if we look at each individually, the sodium atom is losing an electron. Oxidation is loss of electrons. So the sodium is being oxidized. The chlorine is gaining electrons. The chlorine is being reduced. Any questions? When we have a metal and a nonmetal, we have a complete transfer of electrons. But we also have oxidation-reduction reactions involving nonmetals where there is not a complete transfer of electrons. There's an incomplete transfer or a shift in the electron density. If we look at an illustration of a hydrogen molecule and a chlorine molecule, Hydrogen molecule is 2 hydrogen atoms covalently bonded, and the red here illustrates higher electron density. So electron density between the 2 atoms is larger, and between the 2 chlorine atoms is larger. But both of these molecules are very symmetrical. We don't have one end being more positive than the other. When we have a covalent bond between a hydrogen atom and a chlorine atom, the electron density is no longer evenly distributed. There's more electron density around the chlorine because the chlorine is more attractive to the electrons. And so in the process of this reaction, we have a shift where now chlorine has increased its electron density. It hasn't become an ionic compound. It's not an ion, but it has more electron density than it did as a neutral molecule. And hydrogen has lost electron density. So reduction is gain. That means that the chlorine is being reduced. Oxidation is loss, and so the hydrogen is being oxidized. Any questions? When we have these redox reactions between nonmetals, it's hard to identify what's going on. When you have a metal and a nonmetal, the elements, you can see that there's electron transfer occurring. When you have combustion, something reacting with oxygen, you can just know that there's an oxidation-reduction reaction involved. But what if you have 2 nonmetals? It's kind of hard. And so chemists came up with the idea of oxidation states. They're also referred to as oxidation numbers, to keep track of that just shift in electron density. So what is confusing about oxidation states is their strong similarity to ionic charges. Oftentimes the ionic charge and an oxidation state will be the same number, but they are different concepts. Okay, so your child might be playing t-ball and he's 4 years old and his jersey has the number 4 on it. Does that mean the kid with the jersey number 11 is 11 years old? Not necessarily. It was just sort of a coincidence. They happen to be the same, but your age and your jersey number are not exactly the same thing. An oxidation state is not the same as an ionic charge. And what's confusing is it's often the same number. Ionic charges are real and measurable. Oxidation states are completely made up. We made them up to help us keep track of stuff. So we need to learn how to assign oxidation states. And if you can remember that oxidation states are frequently the same number as an ionic charge, that will help a lot. So free elements have an oxidation state of 0. And these rules are in order of priority. So if you get conflicts between, let's say, Rule 1 and Rule 5, Rule 1 wins. So free elements have an oxidation state of 0. In this reaction of sodium and chlorine, both of these have oxidation states of 0. If you have monatomic ions, their oxidation state is equal to their charge, the same number. So sodium ion in sodium chloride has a +1 ionic charge, and it has a +1 oxidation state. Chlorine has a -1 charge, and it has a -1 oxidation state. The sum of the oxidation states of atoms in a compound is 0. So in sodium chloride, where we have sodium and chloride, the oxidation states, +1 for sodium and -1 for chlorine, add up to 0. And that's true for all neutral compounds. So these rules are in your book, and they're posted on Blackboard, and you can go look at them on YouTube later as well. The sum of the oxidation states of the atoms in a neutral molecule is 0. That's kind of redundant with a, in a polyatomic ion, they add up to the charge on the ion. So in nitrate ion, overall this has a -1 charge. The oxygen has a -2 charge. There are 3 of them. So we have 3 -2 oxidation states, And the nitrogen has a +5 oxidation state. There's only one of them. And so +5 plus 3 times -2 adds up to -1. Are you confused? I don't want to assume that people are confused, but usually people are getting confused by this point. Like, what's with all these adding and not positive and negative numbers? It might help if you think of it as you owing people money and people owing you money. It's like people owe me $5, so that's +5 for me, but then I owe 3 other people -2. I owe them $2. So overall, I'm out $1. It's the same thought process. And most of us can do that fine with money that we owe back and forth. But when we talk about oxidation states, we're like, well, what are we talking about? It's the same math. You know how to do it. Okay? You just have to get a little bit familiar with it and practice it. So in compounds, metals have positive oxidation states, just like metals always have positive ionic charges. Group 1 metals are always going to be +1. Group 2 metals are always going to be +2. So far, those oxidation states have really corresponded well with ionic charges. And then we get to number 5, and this is where we deal with things that don't fit in there. So the nonmetals. The nonmetals, when they form molecular compounds, they don't have ionic charges. So how do we figure out what their oxidation states are? We have this order of priority. Fluorine gets to be -1. He gets first choice. Hydrogen gets to be +1. Oxygen gets to be -2. And then we go in order of group number 7, 6, and 5. Now, this is a table that you need to memorize. How do you remember that? Well, this is the best I've been able to come up with. Fluorine, hydrogen, oxygen, 7, 6, 5. Okay, the 7, 6, 5, that's not so hard. FHO reminds me of pho, Asian noodles, right? So pho, it's got the F sound, and so FHO, that's how I remember it. I don't know if that helps you or not. You could come up with something else. Fluorine, hydrogen, oxygen, and then you go in reverse group numbers, 7, 6, 5. So, for example, let's look at, well, no, let's not look at any of those anyway. 2 more comments. Fractional oxidation states are possible. This is a made-up concept. It's not an ionic charge, and so you can have like a +1/2 or a -1/2 charge, oxidation state, sorry. You can't have a +1/2 ionic charge. And we write the sign before the number for the oxidation states. We write it after for the ionic charges. I am not going to nail you on that on anything, but that's how we do it. And so if you're like, why is the minus sign before here and after there? This is why. Because we want to indicate that these are a little different. Let's look at some examples. So we're supposed to assign an oxidation state to each atom in each of these things. So the first one is chromium. Here, chromium is the element, the free element. And so what's the oxidation state? 0. And that's going to be the same as its charge, right? It doesn't have a charge when it's an atom. How about Cr3+, the chromium 3 ion? It's going to be +3. The charge is 3+, the oxidation state is +3. Let's look at CCl4. This is carbon tetrachloride. We have 2 different elements here, carbon and chlorine. And so we have to assign an oxidation state to each. So there's going to be carbon, and then there's going to be chlorine. Well, these are 2 nonmetals. And so there's no ionic charges, and so we have to go to Rule 5, the table. Pho 765. So we don't have fluorine, we don't have hydrogen, we don't have oxygen. The next in the priority list is chlorine because it's in group 7. The group 7 elements get to have an oxidation state that is equal to their ionic charge when they are ions. So the chlorine is going to be -1. Chlorine does not have a 1- charge in this compound. It's not an ionic compound, but the oxidation state is -1. So if the chlorine is -1, we figure out what the carbon is because we know that all the oxidation states for this neutral molecule have to add up to 0. +4, yeah. So if we say, well, let's just say that it's X. So the oxidation state for carbon plus, there's 4 chlorines, and they're each -1. That has to add up to 0. That's what we're doing in our heads. And feel free to write it down on paper if that helps you. So the oxidation state for carbon must be +4. We always write the sign for the oxidation state. So 4 is not good enough. I understand that you mean +4, but you need to put the plus in there. And Mastering Chemistry says it wants the oxidation states as signed integers. Signed means write the sign, plus or minus. So any questions about C?
So anytime you have a situation like that, it will have to equal 0.
Mm-hmm.
The only time it doesn't equal 0 is when you have an ion? Or
Yeah, something like this, a polyatomic ion, then the oxidation states have to add up to equal the charge. Any other questions? So let's look at SrBr2. Well, is that an ionic compound? It is. Ionic compounds are easier because you look at the ion charges. So we've got strontium and we've got bromine. Well, what's the charge on a strontium ion?
+2 +2 +2.
2 plus is the charge. The oxidation state is +2. And bromine, as bromide, has a 1- charge. So we expect the oxidation state to be -1. And then check, do those add up to 0? You've got 2 bromines, so 2 negative charges, and 2 positive charges, yes, they add up to 0. Let's do SO3. Is that an ionic compound? No. It's 2 nonmetals. To have an ionic compound, you need a metal and a nonmetal, except for ammonium. So we're going to have sulfur, and we're going to have oxygen. So again, we go all the way down to Rule 5 in that list, and we think Fa, 765. Well, fluorine? No. Hydrogen? No. Oxygen? Oxygen gets its first choice. Oxygen wants to be -2. That's the charge it takes when it forms an ion. So the oxidation state for oxygen is -2. Each oxygen has its own oxidation state. They're going to be the same, but we're not going to say that the oxidation state for oxygen is -6. They're each -2. So then we can do a little algebra thing here and say, well, the sulfur is X, and we've got 3 oxygens, and they are each -2, and that has to add up to 0. So what's the oxidation state for sulfur? +6. Oxidation states can be confusing, but they actually allow us to identify oxidation-reduction reactions without learning and memorizing a whole bunch more chemistry. And so, in a way, they're a shortcut.
So they can change, right?
Yes, in a reaction, in an oxidation-reduction reaction, they're going to change. One element is going to go up in oxidation state, and another is going to go down in oxidation state.
But as far as for being +6, it's not always.
It is not
just
always
changes depending on the
+6.
compound.
It depends on the compound. Yeah. Fluorine, almost always -1. That's why it's at the top of that list. Hydrogen, almost always +1. And oxygen, almost always -2. And then they go in order. Let's look at the nitrate ion. So we've got nitrogen and we've got oxygens. Again, we're doing the Fa765 because we don't have an ionic compound, we have a polyatomic ion. So no fluorine, no hydrogen, but there's oxygen. Oxygen gets to be -2. And then we have to figure out what nitrogen is. So if we say the nitrogen is X, and we have 3 oxygens, and they each have an oxidation state of -2, what's this supposed to add up to? This needs to add up to -1, because that's the charge on the ion. So this is -6, so the nitrogen must be what? +5. So the nitrogen is +5. Yes?
Okay, so SO3, you know, it's not implied that it's a polyatomic ion if there's no sign showing that, like,
If there's no sign, it's not a polyatomic ion.
even though, you know, you would
Because
think
this
it
is
would.
this compound is sulfur trioxide. It's a molecular compound. There's an ion that looks very similar. It's sulfite,
Right,
but it has a 2- charge.
right.
If we don't put the charge on it, it's SO3. It's
So
the
it's
molecular
just its own
compound.
thing. Okay,
Got to have the charge.
okay.
In sulfite ion, the sulfur is going to have a different oxidation state
Right.
because of this charge. It's going to have an oxidation state of +4. Any other questions? So how do we identify redox reactions when we don't have combustion or the formation of ionic compounds? Oxidation and reduction. Okay, we defined them earlier as oxidation is loss of electrons. When you lose electrons, you increase the oxidation state. So oxidation is being oxidized, it's increasing the oxidation state. Reduction is a decrease in oxidation state. The oxidation state is being reduced. Okay, so there's some clues in the words to what they mean. If we look at this reaction between elemental carbon and elemental sulfur to form carbon disulfide. Here, the oxidation states for both of these are 0. They're elements. And then we can apply the rules from number 5 to predict that the sulfur has an oxidation state of -2 because there's no fluorine, there's no hydrogen, there's no oxygen, so we're going to go group 7. There's none of those. Then we're going to go group 6. And so sulfur's in group 6. Sulfur gets to be -2. And then carbon has to be whatever is needed so that those oxidation states add up to 0. So carbon's +4. So we identify the oxidation states of each of those elements in the products, and then we look and see how they changed. Carbon went from 0 to +4. Its oxidation state increased. That's oxidation. Sulfur's oxidation state decreased. It was reduced. It went from 0 to -2. And so we say that the sulfur is reduced and the carbon is oxidized. Does that make sense? Sort of? Blank stares. So let's do one for practice here. Use oxidation states to identify the element that's oxidized and the element that is reduced in the following redox reaction. So we need to go and look at each element and identify what its oxidation state is. Well, let's start with tin. What's the oxidation state of this guy? 0. It's an element. It doesn't have a charge on it, right? Its charge is 0, its oxidation state is 0. And let's look here, HNO3. Okay, so we have to go, there's no fluorine, there's a hydrogen. What does hydrogen get to be? +1. Then next up is oxygen. So oxygen gets to be -2. And then nitrogen picks up the slack. So we've got +1 for the hydrogen, and we've got 3 oxygens, and they're each -2. And then we've got X for our nitrogen, and that has to add up to 0. So here I've got 1 minus 6 plus x equals 0. So this is minus 5 plus x equals 0. So x is what? Plus 5. I'm going to write him above because it's getting a little crowded down there. So the nitrogen is plus 5. Tin oxide. Okay, this is an ionic compound now. The oxidation numbers are going to be the same as the oxidation. The oxidation states are going to be the same as the ionic charges. Even though the concept is different, the numbers end up being the same numbers. So what's the charge on oxygen as an ion? 2 minus, right? And so its oxidation state is minus 2. What's the charge on this tin ion? Plus 4. The charge is 4 plus, the oxidation state is plus 4. Any questions? NO2. 2 nonmetals. Who gets priority? Oxygen. Oxygen gets what it wants. It wants to be minus 2. There's 2 oxygens, so what does the nitrogen have to be? Plus 4. And then we have water. Who gets priority between hydrogen and oxygen? Hydrogen. So hydrogen gets to be plus 1, and then the oxygen ends up being minus 2. So oxygen still ended up getting what it wanted. So we identified the oxidation states. Get rid of that. Now, to identify what's being oxidized and reduced, we have to look at things that are changing. So let's compare tin as a reactant with tin as a product. What's happening to its oxidation state? Loss of electrons. Oxidation is loss of electrons, or we can look at the oxidation state is going up. It's increasing. So this is being oxidized. Hydrogen is plus 1 here, is plus 1 there. Nothing happened to the hydrogen. The oxygen, minus 2, minus 2, minus 2, minus 2. The oxygen didn't change. What did change? The nitrogen. So here we have the nitrogen. And the nitrogen's oxidation state did what? It went down. It decreased. It was reduced. So the nitrogen is reduced. Any questions? Identify the oxidation states for each element and then look for the ones that are changing. It is possible for more than 2 to change, but we probably won't see much of that in this class. So oxidation and reduction must occur simultaneously. If one thing loses electrons, another one has to take them. Very important. Now, as if all of that wasn't confusing enough, we sometimes refer to reducing agents and oxidizing agents. The reducing agent is the reactant that causes another element to be reduced. The reducing agent is the element that gets oxidized. So that's confusing. Let's think about Hollywood and movie stars and movie agents. Does the movie agent star in the new blockbuster movie? No. The movie agent arranges for the movie star to star in the movie. He doesn't actually do it himself. The reducing agent isn't reduced. He arranges for something else to be reduced. Same with the oxidizing agent. The oxidizing agent oxidizes something else. The oxidizing agent is reduced, not oxidized. So the oxidizing agent contains the element that is reduced. Okay, so we're going to practice identifying redox reactions, identifying oxidizing agents and reducing agents. So first thing we have to do is say, is this a redox reaction? And next we need to identify the oxidizing agent and the reducing agent. So if we look at this first reaction, is this a redox reaction?
No. Yes.
Yes. So how do we know that? Well, we could go through and assign oxidation states. We're going to have to do that to look at the, well, we don't have to, but we probably should do that to identify the agents in here. But here we have a metal and a nonmetal, and they're forming an ionic compound. Ions are being formed. If we go from atoms to ions, there has to be loss and gain of electrons. So this is a redox reaction. So we could look at it based on charges. We can do that with ionic compounds. We can't with molecular compounds. So this is the formation of an ionic compound, and so we can look at the ionic charges. We don't have to go and look at oxidation states. So in this compound, we've got lithium plus and chlorine minus. And so we see that lithium is going from 0 charge to +1, so it lost an electron, right? Oxidation is loss of electrons. This is being oxidized. So lithium is oxidized. What's happening to the chlorine? The chlorine is being reduced. Reduction is gain of electrons. The chlorine is gaining electrons to become an ion. So chlorine is reduced. So we're identifying things here, but we haven't answered the question. It wants the oxidizing agent. Lithium is oxidized. Lithium is starring in the movie. Chlorine is getting it that job. Chlorine is the oxidizing agent. I'll call it ox agent. And then lithium has to be the reducing agent. Yes?
I would think of whenever there's a metal and a non-metal, I was thinking that the metal is the one that's going to get oxidized and the non-metal is the one that's going to get reduced.
Yes, yes. The metal will always get oxidized because it's going to form a positive ion by losing electrons. And nonmetals going from a neutral molecule to an ion will always be reduced. Any questions about number 1? Let's look at number 2. Is this a redox reaction?
Yes.
Yeah. Look at aluminum. Here it's an atom, and over here it's an ion. Here we have a metal ion, and we're going to a metal atom. So the aluminum, the element, is being oxidized. It lost electrons. So aluminum is oxidized. That makes it the reducing agent. The tin ion, tin 2, is gaining electrons to become a neutral atom. So the tin ion is reduced. Therefore, it's the oxidizing agent. Is that making any sense? The most important thing is getting the oxidizing and reducing down, the oxidation and reduction. If the agent business is just too much for you, you'll be okay. That's not such a big deal. Okay, let's look at this one. Here we've got lead nitrate and lithium chloride reacting to form lead 2 chloride and lithium nitrate. Well, these are ionic compounds. We don't have to use oxidation states. We could, but we don't have to. What's the charge on this lead ion? 2+. So this is Pb, 2+. And what's the charge on the lead ion over here? Still 2+. Was that oxidized or reduced? Nope. How about nitrate? Did that stay the same? Yeah. We have NO3 minus on one side and NO3 minus on the other side. That means nothing inside of nitrate changed. How about lithium? Here it's +1, and over here it's still +1. Was it oxidized or reduced? Nope. How about chloride? Did chloride get oxidized or reduced? No, because here it's an ion, -1 charge, and here it's an ion, -1 charge. Is this a redox reaction? No. No electrons were transferred. Is it a chemical reaction? Yeah. It's a precipitation reaction. We're forming lead-2 chloride, which is insoluble, but it's not a redox reaction. So that one's not redox. So when you've got ions involved, you can look at ionic charges, and that's probably easier to get your mind around. But then we look at this one down here, carbon and oxygen reacting to form CO2. Is that an oxidation-reduction reaction? Yeah. You have a nonmetal and you have two nonmetals reacting. That tells you it's an oxidation-reduction reaction. It's also a combustion reaction. So here we have to use oxidation states. What's the oxidation state for carbon? Well, over here, the carbon by itself is 0. And how about this oxygen? 0. Because it's an element, right? And then we've got carbon dioxide. Who gets priority, carbon or oxygen? Oxygen. So oxygen gets to be -2. What's the carbon? +4. There are 2 oxygens. They are each -2. And so we've got -2 and -2, and these have to add up with this to be the whole thing. So what is happening to the carbon? It's being oxidized. So is it the oxidizing agent? No, it's the reducing agent because it's being oxidized. And oxygen is going down, decreasing, reducing its oxidation state. It's being reduced. Oxygen is the oxidizing agent.
So carbon is acting like the metal in this case?
Well, not really. We can't really say that carbon's acting like the metal, but the carbon is being reduced, and metals are often reduced. It's not forming ions. It's not an ionic compound. Carbon does not have a +4 charge. It did not lose 4 electrons. But electron density was shifted to the oxygen.
So from the previous slides, is that referring to that it's more negatively charged on the oxygen side? Or I don't get that part.
Well, it turns out that carbon dioxide is a symmetrical molecule. But there's going to be, I don't know how to represent this. See how this looks. There's going to be more electron density on the oxygens and less on the carbon. Any other questions? The electrons are still shared, but they're not shared equally. Combustion reactions. So we've mentioned these. We have a substance reacting with oxygen to form one or more oxygen-containing compounds. Often, one of these is water, but not always. And combustion reactions also emit heat. And we should know that pretty easily. Combustion is a different word for burning. When stuff burns, it gets hot, right? So natural gas is mostly methane. When it reacts with oxygen, it forms carbon dioxide and water. And here, we've had enough practice. We've got the oxidation states. Here, carbon is -4, and over here, carbon is +4. What's happening to the carbon? It's being oxidized. The hydrogen here is +1, +1 over there. The oxygen is going from 0 to -2 and -2, and so the oxygen is being reduced.
That's a violent reaction.
This is a violent reaction. It's also a very useful reaction. We used it to cook dinner last night, right? Your gas stove, this is what's going on. gives off a lot of energy. Writing equations for combustion reactions. Most of the combustion reactions we're going to ask you to write are for organic compounds that contain carbon, hydrogen, and oxygen, or just carbon and hydrogen. And so what you need to remember is that the products are going to be CO2 and water, always, when you've got carbon compounds burning, provided you have enough oxygen, which we do in these cases. So to write the balanced equation, let's not write with the highlighter, C2H5OH. Combustion means this is going to be reacting with oxygen. We're not specifically telling you that the other reactant is oxygen. You need to know that. In a combustion reaction, oxygen is required. And then the products are going to be the same, CO2 and H2O. And then we have to figure out how to balance it. So we might want to start with the carbons. Here we have 2 carbons, and we only have 1 carbon on the right. So if I put a 2 in front of the CO2, I've got 4 carbons on each side. I'm sorry, 2 carbons on each side. And then the next thing we probably want to do is the hydrogens. Oxygen is all by himself here, and so we probably want to leave that one to last. So over here I have 6 hydrogens. I need to make 6 hydrogens over here, so I'll put a 3 in front of water. Now, how many total oxygens do we have over here on the right side? 7. We've got 4 here and 3. So we've got 7 oxygens over there. And over here on the left side, we've got these guys that are coming in pairs, and we also have 1 over here. So we need to end up with 6 here plus that 1. And so we're going to put a 3 in there. That's it. This was an easy one. Combustion reactions are often where you get into that odd-even problem, and then just double everything and it'll go away. And sometimes you end up with coefficients like 25 or 30, and students sometimes find those alarming, but it's okay. Just get it balanced, and then when you're all done balancing and the numbers look kind of high, just see, could it be reduced? Maybe it can, maybe it can't. Any other questions?
The H2O usually a gas in that reaction?
H2O would be a gas, bless you, because when we think about this, this is a combustion reaction, it's going to be hot, right? If it's giving off heat, the water is probably going to be in the gas state.
When you turn on the stove and you put a pot,
Yeah, you put
like a stainless steel pot.
and you see condensation, right?
Yeah.
Next, if you have a gas stove, the next time you turn it on, you put the pot on there, the pot's cold, you turn the burner on, you'll see condensation on the sides of the pot. Where's that water coming from? It's coming from the combustion reaction. It forms water in the gas state, and as it comes up and hits the cold pot, it condenses on the pot. Once the pot warms up, it just goes off into the air. End of chapter 4.